Hello everyone, welcome to Physics Unwrapped YouTube channel. In this channel, you will get concepts related to physics as well as PYQ of various examination. In today's video, I am going to continue solving KSET 2025 Physical Science question paper. Let us start with the 46th question. In the question, what we have, if x and p are the position and the momentum operators of a particle, then the commutator of x square comma p square. So we need to find the commutator of x square comma p square. They have given four options. Let us solve this. We know that actually there is a general form, that is commutation of x comma p is nothing but I into h cut. Now we know that the commutation of x comma p, which is nothing but I into h cut. Here we have x square and p square. Now using the identities, we shall solve this problem. So what is the identity? That is commutation of a comma b c. That is a b c or the operators. We can write like this. That is a comma b into c plus b comma b into a comma c. So we can write like this. I have already given these identities in the Poisson brackets. You can go and check the classical mechanics playlist. Now according to this identity, I am going to expand this commutation of x square and p square. This p square, I can write it as p into p, right? If I write p into p, it is of the this form. Now after solving this, I got x square comma p into p plus p into x square comma p. This is what I got, right? I'm taking this to be my equation 1. Now I'm going to solve this commutation of x comma p now. Now what is the commutation of x square comma p? Now according to this identity, again if I expand this, I'll get x comma p into x plus x into x comma p. This is what we get now. But we know that x comma p is nothing but I into h cut. So I into h cut into x plus again x into I into h cut. So what is the solution we are getting? It is 2 times of I into h cut into x. We got this. So apply this 2 in 1. If I substitute 2 in 1, what I get? Commutation of x square and p square is nothing but, instead of x square comma p, what I can write? 2 times of I into h cut into x into p plus, first we have p into commutation of x square and p. So commutation of x square and p is again 2 times of I into h cut into x. In this equation, I can take I into h cut into 2 common, right? So I am taking 2 times of I into h cut common. What is left inside the bracket? It is xp plus px. Now can I write this xp plus px, which is equal to 2 times of px? No, I can't write like this. Why? Because operators does not follow the commutative law. That is, xp, it is not equal to px. So we need to keep the answer in this way only. Now look at the options. They have already given here 4I h cut px. This is wrong option. Don't mark for this. We shall go for the second option, that is 2 times of I h cut xp comma px, where x are the position and the momentum operators. Yes, let us move on to the next question. What we have in the next question? Let xi of n l m r vector denote the eigenfunction of a Hamiltonian for a spherically symmetric potential, that is v of mod of r vector. then psi of n L M R vector, that is equal to 1 by 4 times of psi of 210 plus square root of 3 psi of 2 1 minus 1 and square root of 12 psi of 2 1 1 is a state which is an eigenfunction of the operators. So this is a very easy question, and it looks like complicated bit. Now let us solve this question. They have given this state, and we must find this state is an eigenfunction of the operators. They have given here operators, that is a Hamiltonian operator and L square, and they have given LZ. These three are the three different set of operators. Now when operator acting on the state function, that will give rise to a eigenvalue and again the state function. Now I'll write for first Hamiltonian operator. When Hamiltonian operator acts on the state function, that is psi of NLM, that gives rise to an eigenfunction En. Okay, then eigenvalue, this is an eigenvalue, and again the state function, that is psi of NLM. So when the operator which is acting on the state function, which will gives you the eigenvalue, and again the state function will remains as it is. This is what it tells. Now what they are asking, this state function which is an eigenfunction of which operators. So this eigenvalue, it is depending on what? N. It is depending on the n, that is a principal quantum number. Can you see in all the states we have n value to be equal to 2? Yes, can you see it is psi of 210, it is 2, here also it is 2, here also it is 2. I can say shortly that all these terms have the same principal quantum number. So H is a it is a state which is an eigenfunction of the operator H. So H is verified. Now what about L square? We shall see for L square, right? Now when this operator L square, which has acted upon the state function I of n L M, which will gives rise to a eigenvalue, that is eigenvalue L into L plus 1 into H cut square into psi of L n L M, again the state we will get. So this is a eigenvalue, that L square operator depends on the eigenvalue L into L plus 1 into H cut square, right? And now what we have in place of L, that is NLM, it is in the form of, that is a midterm. In all three states I can say that midterm is equal to 1, that is L which is equal to 1. If in all uh, three terms have the same L, I can say that given state is also an eigenfunction of L square, right? Now L square is also obeyed. Now we shall see for LZ operator. When LZ acted upon psi of NLM, that is a state function, given state function for a spherically symmetric potential, that gives rise to a eigenvalue M into H cut psi of NLM. This M is a magnetic moment quantum number. Here L is a orbital quantum number. Okay, so what is here M in the all three state functions we have 0, -1 and 1, right? So M can take the value 0, -1 and +1. So we have three different values. So I can say the state which is not an eigenfunction of the operator LZ. Now only H and L square is verified correctly. I can tick to the option 2. Option 2 is the right answer. Let us proceed to the next question. What we have in this question, that is the Hamiltonian of a two system is given by H, which is equal to E002. It is a 2 cross 2 matrix, I can say. When it is subjected to a time independent perturbative Hamiltonian, that is H prime, which is equal to 0 epsilon epsilon 0, where E is small compared to the capital E, then the lowest order correction to the energies of a two systems are given by. This is also easy question. It comes under perturbation theorem in quantum mechanics. Yeah, let us solve this question. They are asking here lowest order correction. What this means we need to go from first order correction. This is second order correction. For a first order correction of the energy, we have the formula, that is En of 1. which is equal to bra of n into h prime into ket of n. This is the formula for the first order correction. Here n can take the value 1 and 2. Okay, n, these are the states that can take the values n to be equal to 1 and n to be equal to 2. First, we will substitute for n value to be equal to 1, that is bra of 1 into h prime into ket of 1. So on solving this, I get the value to be equal to 0. Or simply you can see here h prime, it is a diagonal element. These are the off diagonal elements, right? Here can you see this diagonal elements are 0 and 0. We have a short trick, or you can say logically, this first order correction only depends on the diagonal elements of h prime. So this diagonal elements are 0. I can get, if n value which is equal to 1 means it is 0. For n value which is equal to 2 also, I'll get the solution to be equal to 0 itself. I'll solve 1. How it will form? So what we have bra of 1 into h prime into ket of 1, right? Now what is the h prime value? It is 0 epsilon epsilon 0. Now tell me what is the bra value. This is nothing but in the matrix form we can write it as 1 0. Okay, the ket value it is like this 1 0. Okay, so these are the forms of ket and bra in terms of matrix. Now first we will do h prime, that is 0 epsilon epsilon 0 into ket of 1, that is 1 0, same as matrix multiplication. So if I do, what I'll get, this is bra of 1, I'm going to write as it is. First it is acted on the right side, then the result it is acted to the left side. And now what happens, 0 into 1 is 0 plus epsilon into 0 is 0, epsilon into 1 is epsilon plus 0 into 0 is 0. This is what we got. Here it is a 2 cross 2 matrix, here it is 2 cross 1 matrix, right? The result we need to get in terms of 2 cross 1. So we got ket of bra of 1 which is equal to 0 epsilon. Now what is this ket of 1? How can I write it as? It is 1 0 row matrix into 0 into epsilon. Here it is 1 cross 2, here it is 2 cross 1, right? So we'll get the solution to be equal to 1 cross 1. So that is a 1, only one number will be possible. 1 zeros are 0 plus 0 into epsilon is 0. So we got the solution 0. I'm here writing directly. For 2 also we'll get the, instead of n you keep 2. So what is the value for 2? Get to 2 in the form of matrix is nothing but 0 1. Okay, so like this, for a lowest order corrections, that is we did for a first order correction. For first order correction we got both the energies, for both the states the energy values to be equal to 0 0. They have said it is two states, so we consider the both the states to be equal to 1 and 2. The energies we got 0. In no options it is 0. So let us go for the second order correction. What is the second order correction? It is given by the formula E n of 2, which is equal to summation m not equal to n and magnitude of bra of m into h prime into ket of n whole square divided by E n of 0 minus E m of 0. Okay, here they are saying m not equal to n. So this is ket of bra of m into h prime into ket of n. Same as before we did, I'm going to do now. I'm considering n value which is equal to 1 and m value which is equal to 2. This let it be the case 1. So instead of n, what it will be there? It is 1 to the power of 2. What it is saying means that 2 says it is a second order correction. In the previous slide, here 1 says the first order correction. Same as here in this slide, the 2 represents it as a second order correction. So instead of m, I'm keeping that as 2, magnitude of 2 into, instead of h prime, we can substitute for 0, epsilon, epsilon 0. Okay, next, instead of n, I'm keeping it as 1, right? It is mod of whole square divided by en. For this is a unperturbed state, that is for h we are seeing en means e1 of 0 minus e2 of 0. So by the logic I can see 2 1, 2 1 in the sense what, here it will be in matrix it is 1 1 mn. In terms of mno it is 1 1 1 2 2 1 2 2, right? So here we having a 2 1, 2 1 can take the value epsilon, so it will be mod of epsilon square, it is epsilon square only. E10 means 1 1 here, n value is also 1, um, m value will be equal to 2, so 1 1 1 1 value is e minus e2, e2 in the sense 2 2, so 2 2 value is 2e. By logic we can do this problem very easily. It is epsilon square divided by minus e will be the solution for e12, that is um, state 1, that is n which is equal to 1. Now we are taking n value to be equal to 2 and m value to be equal to 1. Why? Because m is not equal to n, that is the condition. If I take like this, we will get the solution. Above we will get the epsilon square, below you will get, instead of n it is 2, so 2 2 means 2e minus of n which is equal to 1, 1 1 means e, right? So I get the solution to be equal to epsilon square divided by e. So these are the, where we'll go back to the lowest order corrections to the energies of this two states are given by minus epsilon square divided by e and epsilon square divided by e. That is option 3 is the right option. So once I showed in the normal method, so this we can do using the matrix, that is a matrix method also we can follow and we can do. Yes, let us move on to the next question. What does we have in this question? A sealed and thermally insulated box. Yeah, let us consider a box which is thermally insulated, it seems, of a total volume. This is having a complete volume to be equal to 2v, is divided into two equal parts. Yes, it is divided into two equal divisions by impermeable wall. This impermeable wall means there is no heat exchange. Heat exchange means delta q which is equal to 0. If delta q which is equal to 0 means the work done will be 0, right? Yes. Now, let us study the question. The left half of the box is occupied by n moles of gas molecules at temperature T. Now, identify the entropy we need to find. That is S we need to find. When the wall is suddenly removed, if this wall is suddenly removed and gas expands to fill the entire volume of the box. Now, if this work done is 0 means we will get the temperature to be equal to also 0, that is a change in temperature. If change in temperature is 0 means the internal energy will also be 0. Because why? Because internal energy only depends on the temperature. Now what we are observing in this question, it is a reversible process, it can't again be formed. Means if we remove the wall, the molecules will shift to this side also and it will arrange in the total volume 2v. So this process is reversible, but we can apply the formula for entropy in reversible process for an ideal gas. That formula we have, that is equal to delta S, which is equal to nr into ln of V final divided by V initial. So what is this n? It is a number of moles. What is r? R is a universal gas constant, and ln, it is a anti-logarithms V final, volume final divided by V initial, right? V initial, the volume we were having, it is divided into two equal halves, so volume is completely divided. V initial will be V and V final will be 2V, right? Now delta S, that is change in entropy, which is equal to number of moles we have is n. R is a universal gas constant. Ln of V final is 2V divided by V initial is V. V get cancels. What is left? Nr ln of 2 is the change in entropy. So which is the correct option? Option 3 is the correct option. Thank you for watching. For more videos, you can visit my channel, that is Physics Unwrapped.